Hello. Today I'm going to talk about phases of the design process of unmanned aerial system. So this is the first step in the design process of any types of aerial object. So this is going to be our today talk. Generally there are three different phases once you want to do any design of any engineering system. It starts with the needs, with the requirement, what we are looking for, and then we have the acquisitions phase and we have the utilization phase. So based on the need, there are four different steps that we need to consider once we want to design in any aerial object. So the first step is conceptual design. The second phase is preliminary design, and the third phase is detailed design, and the last step is production and construction. And in the utilization phase, we have product use, we have support and disposal. So these are the main steps that we need to follow in order to design an optimized system that can be aerial system or ground system or underwater system. So these phases of the design process works for any system. Again, consists of three different parts: needs, acquisition phase, and utilization phase. So this flowchart that you will see here shows a relationship between different design activities. So as we see here, the needs are the first step that needs to be determined in order to design an optimized system, which are the design requirement. So after we know our design requirement, we proceed with the conceptual design. So in the conceptual design, we actually conceptualize our system. So for example, if you want to design a passenger aircraft, or if you want to design a fixed wing drone or flapping wing drone, we need to know what configuration or what concept we are proposing. And then after this, we have the preliminary design. And after the preliminary design, we need to do a detailed design, which actually will get the actual size, the optimum values for each parameter during this design process. And then after we finish our design process, we need to do the manufacturing process and the fabrication. And then we eventually will do the test and evaluation. So if they satisfy our design requirement, so here, this is the last step of our process. And if not, we need to revisit our design requirement and again, optimize each step in order to satisfy our requirement. So usually after this step, we need to perform different types of optimization process to have optimum design. So conceptual system design, this is the first step in the design process of any aerial object. So here in this case, we need to develop and define a specific design requirement for the system as the entry. So for example, if we look at this configuration of this airplane, you see that this is not similar to concept that we are seeing in our daily life. So somehow it is a strange design, but this is based on a need. So we need to know for what we have designed this type of aircraft. So in the conceptual design, there are different steps that I am going to explain this flow chart as we can see here. Again, if any design process test is started based on the design requirements. So here is problem definition and need identification, or our design requirement. And here we need to perform a constraint analysis. So once you are designing in a drone or any aerial object or aquatic system, we need to know our constraints. So we need to know our weight limitation, we need to know our size limitation, we need to know, for example, the flight time or the operating time. So these are the factors that we need to consider once we want to start our design process. Then we will do the functional analysis. So for example, we can define a cost analysis to see that how we can optimize our system based on a our need or requirement or design requirement, and based on the cost analysis. So then we will investigate the system feasibility study, and here then we will come to identify the technical performance measure. So here we can, after this stage, which these are all needs that need to be satisfied, we can propose different concepts. So we can have, for example, this is one concept for a specified mission. So we can have here as an example 5 different concepts. So for each concept, then we need to specify the system requirement and system specifications, which eventually leads us to set the relative importance of technical performance measures. Then we need to identify the areas of the risk and uncertainty. We need to identify the evaluation techniques. We need to run the sensitivity analysis. We need to evaluate design alternative, trade-off analysis to select the best concept, and then we will see our conceptual design, or we review our conceptual design. And if this pass, we will go to next step, which is the preliminary system design. So this step that we see here is a conceptual design in such a way that we conceptualize or the configuration of our aerial object or our drone or any other system. Actually, this methodology works for any system. So in case that if our conceptual design review failed, we need to select a new approach. It means that if we see this, we will get back to the new concept. So here we will start with concept 2, and then this is an algorithm or flowchart that we follow up in order to have an optimized system in such a way that we can actually accept our conceptual design and move to the next step, which is the preliminary design. So getting back to this figure that you will see here. So as we said, we have the design requirement that need to be satisfied during any design process. So here, this is another steps that we can see. Definition, which is actually somehow our concept. So we have the concept, we have the pre-design, and eventually we have the design, and then we have the manufacturing process, and then we have the maintenance, which was the acquisition phase of our design. So here there are, in the design of any aerial object, there are different parts that we need to consider. So the first of all, we need the physical properties of the flight vehicle. So for example, what should be the flight speed of our aerial object or drone, or it can be manned or unmanned vehicle, aerial vehicle, or it can be the flight altitude that our system can fly. It can be the flight time, how long our drone is going to fly. And also it can be, for example, the area or the atmosphere that our vehicle is supposed to fly. So for example, if you fly in a Martian environment or Venus, the atmospheric conditions are totally different than the Earth. So for example, the temperature, the pressure, the type of the gases that we are dealing with, so everything is different. So therefore, this is the physical properties of a flight vehicle is something that we need to specify before designing our system. So then we need to know our sizing process or airframe structure that we are designing our system. Then we need to run different types of aerodynamic analysis. We need to design a proportion system for our design, and eventually have a flight control for our system. So these are different steps that we can consider them once you are doing the conceptual design. Because for example, I'm going to show you in the next slide that once we design a drone, a fixed wing drone or fixed wing aircraft, so we need to know the configuration of our system. So the type of the proportion system, the shape of the structure, or the type of the control systems actually determines are determined in this phase of design. So the preliminary system design is the next step after the conceptual design. So by the end of the conceptual design phase, usually we need to evaluate our design by addressing some of the most fundamental system characteristics. So the essential purpose of the preliminary design is to determine the feature of the basic component and the subsystem. So for example, we are determining the size of the wing, some of the aerodynamic characteristics. We can run different types of aerodynamic analysis. We can select our propulsion system. We can do a CAD modeling of our system. So these are the preliminary system design of our aircraft. So the preliminary design phase includes different steps that I'm going to mention them in this slide. So the first of all, we need to develop design requirement for the subsystem. So what are the subsystem in an aerial object? So for example, if we look at this aircraft, we will see that it is consisted of wing. We have a fuselage here. We have our propulsion system here, and we have vertical tails, and we have the horizontal tail. So we need to develop a design requirement for each of this subsystem. In the second step, we need to prepare development, process, and material specification for the subsystem. So each part of this aircraft or the subsystem is consisted of different material. So here we can apply different material for manufacturing of this system. So why we need this material selection in this stage of the design? Because it eventually affects on a structure analysis and also on the aerodynamic characteristics of our system. So here, this is the reason that we need to specify that what type of material we are going to use for our system, which can affect on the weight of our system, which is one of the main factors in the design process of any aerial object. So determine the performance technical measure at the subsystem level. We need to know that how the performance of different subsystems, for example, our propulsion system, are changing in different altitudes. So one of the things that we are going to see in the future is that once you want to design an aircraft or a drone or a fixed-wing UAV or unmanned aerial vehicle, we know that the efficiency of the engines, which they are providing the required thrust force for our aerial object, is somehow depend on the atmospheric characteristic. So for example, if I have two engines here, they have the propeller, the efficiency of these engines when this aircraft is near the ground is totally different once this is flying, for example, in 10,000 kilometers from the sea level. So this is something that we need to specify during the preliminary system design. So then we conduct functional analysis at the subsystem level. So we need to have an analysis for each subsystem of our aerial object. We need to establish detailed design requirement, and we eventually need to identify appropriate technical design tools, software, and technology for the design process. So about this stage, so in order to design an aircraft, we always need a CAD modeling software like the SolidWorks, like the AutoCAD, or ProEngineer, NX, CATIA. There are plenty of the CAD software that we can apply in order to actually model our aircraft and run different types of analysis. So here we need to identify different types of the tools and the software or technologies that we are going to apply in order to design our system. So one of the things that I want to mention here, during this course, we are going to work with the software which is called XFLR5, which is an open source software that we will go over that, and we will learn through this material that I am teaching in this class how to design and analyze an aircraft in this software. So this is one of the tools that we need to apply during the preliminary system design. So the next step in the design process is detailed system design. So during the detailed system design, we actually are going to select the different components that they are going to install in different subsystems of our aerial object. And since our system is composed of different parts, so we need to have a well designed process for each component. So as we said, after the preliminary design, we have the detailed uh, system design that we need to have the analysis for subsystem, the functionality of the subsystem, then we have the design of the subsystems. So then we will see that if the requirements are met or no, then we have, if yes, we will need to design our component. Again, we review our meet requirement. If the requirements were satisfied and were met, we design the parts and element, and after that, we have the mathematical modeling and the prototype testing and evaluation of our system, and then we will review again our design for approving or rejecting the whole process. And if this works, eventually during this design and detailed system design, we need to release the documentation, which is the CAD modeling or the drawing of our system, which is eventually goes to the manufacturing process. So if we want to summarize this design, the preliminary design process, so during the detailed system design, we are going to specify different components, their location, their sizes, and this is a finalized design. During this detailed design, the position of different components is so important, specifically once you want to determine the center of gravity of our system, which is important for the stability. So I'm going to talk about this with more details later on. So these are something that eventually gives up some drawing or some documentation after performing different types of analysis, and it's ready for the manufacturing process, which is the next phase of this design process. So generally in the system, there is a relation between the design influence and the design actually objectives. So here for the system engineering and aerospace engineering, there is always different. So as we can see here, for the system engineering, the design influences is high in the conceptual design phase and in the preliminary design. But in the aerospace engineering system, what is important here and it influences more is after the detailed design. So in the development phase for any aerospace engineering, the design influences is higher. So here, this is a comparison between the system engineering and the aerospace engineering. So we need to have more realistic and more reliable design for the aerial object or aerospace engineering, because they are working in the space or in the air, so we don't have too much control on them because the type of the material that they are used on, they are used, or their specification, their speed. There are different factors that they are acting actually on design influence. So this is this graph that we can see here. It shows that how the design influence is changing from the low to the high level for system engineering and aerospace engineering. So there are different design requirements in the design process of any aerial object. So this consists of performance requirements, so what we are requiring for our airplane. A stability requirement, it means that our aircraft or our drone should be stable in different axes. Handling requirement, operational requirements, affordability, reliability, maintainability. So for example, once you are designing a system, our system should be reliable and it should be affordable. It should be, maintainable. So these are some requirements that is so important to consider as the design requirement. You have productability. So for example, we don't want to design a drone which we cannot manufacture it, right? So we need to consider that before design process, and I mean during the conceptual design phase, which its inputs are design requirement. So evaluability requirement, usability requirement. So we want to design something which is usable, right? We don't want to design something that nobody can use it because it doesn't make sense. So safety requirement is so important, specifically in the larger size drones or larger size aerial object. The crashworthiness requirement. So for example, if we design a fixed wing drone like this, right? So what is the crashworthiness requirement for this? This is a small and cheap drone. So if this crash, right, we are not going to lose too much money. But if we design a big airplane with a very, very expensive equipment, so we need to consider this crashworthiness a requirement. The supportability and the serviceability requirement is something specifically for the bigger size drone. The sustainability requirement, disposability requirements, marketability requirements, specifically once you want to actually commercialize our design or our system. So environmental requirements is so important, because once we are designing an aircraft or we are designing a drone which is using the fossil fuel, we need to always consider the environments, right? What effects our design is going to have on the environment. Detectability requirement is so important. So for example, if we are designing a military drone or military UAV, we need to consider this detectability. I mean, if our system detected by radar and it attacked by rockets, so we are going to lose our mission. So here, if we are thinking to design a military system, so we need to consider all of this type of the requirements, a standard requirement and a legal requirement. So for example, once you are designing an aircraft, if its size exceeds from a specified size, we need to obtain the legal requirements. So FAA rules are something that need to be considered during the design process. So these two pictures that we will see here, it shows how these requirements have not been met during the design process. So for example, you see here the motor, one of the engines of this aircraft has been failed. So if you want to discuss what type of the design requirements have not been met here, so it can be the performance requirement, means that our propulsion system hasn't had the performance requirement. The reliability requirement has not been met because this system is not reliable because one of the engine has failed. The maintainability requirement, I mean, maybe has been met if this airplane wouldn't crash, so they can replace this engine. And the safety requirement has not been met because it has been failed because of the failing the engine. And sustainability requirement again has been failed because it seems that the airplane is new and the motor has been failed. So this is something that has not been met again. And then for the second picture, as we can see here, so this is using the fuel engines. I mean, imagine that this is a pollution coming out from the aircraft. So this environmental requirement has not been met during the design process, which can eventually say that standards requirements also have been failed during the design process. So these are all the design requirements that we need to consider before designing any type of aerial systems. It can be drone, fixed wing drones, or it can be the passenger aircraft. So during this course, since our focus is on the drone, so we will talk in the future more in the design process. Actually, design process for the fixing UAVs or drones are similar to the aircraft. And since I want to give you overall view, this is the main reason that I also included in this course the design process of any type of the aerial objects. So the aircraft major components and the design requirements is the other topic that we need to consider during the design process of any type of the aerial object. So these are the different type of categories or categories of the design requirements that we are going to talk about them and see that what parameters are actually coming from this design requirements, or what are the output of this design requirement for the process. So the first design requirement is payload, the weight requirement. How much payload should be carried out by our system? So for example, if I am designing this fixed wing MAV or micro air vehicle, during the design process of this, I need to consider that how much weight should be carried out by this system. So for example, if I design a passenger aircraft, my payload is going to be cargoes and plus the passengers. So these are the weight requirements that we need to consider before designing any system. So the output of this design requirement and the components that is affected most is maximum takeoff weight, because depend on the weight of the payload or the weight of the passenger or the cargo, the maximum takeoff weight of our aerial system is changing. So the second one is a payload volume and geometry requirement. So for example, if our payload is a cargo or is a passenger, so the volume and the shape of our payload is different. So for example, if you look at this, if I have some sensor, I want to put them inside of this fuselage or the body. So this is so important what size I am considering here. So this airplane that you can see here, actually this fuselage has been designed to keep the electronic equipment like the sensors, autopilot system, and the camera. So once you're considering this fuselage, so here the size of this fuselage is affected by the size of the cargo or the equipment. So this is so important once you consider this. There are a bunch of the passenger aircraft or cargo aircraft that the shape of their payloads are totally different and unconventional, and this creates our design to be different than the other aircrafts. So I want to open the Google and show you an example of the cargo airplanes to see that how this is going to be changed. So if I show you here the cargo airplane, so you see here, this is one of the cargo aircraft that we see, and you see that the shape of these cargo aircrafts are totally different, and the shape of their fuselage is different because the type and the size of the cargos are different. So these are some examples that you can see here. So going back to the third requirement is the performance requirements, including the maximum speed, the rate of the climb, the takeoff, run, the stall speed, the sailing, and the turn performance. So these are the criteria that they are actually affecting in our system. So what are the performance requirements? So for example, before the designing our system, we need to know that what is the speed of our system. So for example, are we designing a system which is flying with a lower speed like this fixed wing micro vehicle, or with a higher speed like the hypersonic or the supersonic range of the speed? The rate of the climb, with what rate our airplane is going up, is important. The stall speed is important. Stall speed is the minimum speed that our airplane can have. So we all talk more fundamental behind this type of parameters that they're affecting during the whole design process. So the stall speed is the minimum speed of airplane, that if our airplane fly with a lower speed than the stall speed, so our airplane eventually would crash. So the sailing is the altitude or elevation that our airplane is flying, and the turn performance, it means that in what radius our airplane can turn. So for this design requirement, the engine, the landing gear, and the wings are the parameters that they will actually affecting by this design process. So the stability requirements is something that needs to be considered. So the stability, any airplane which is flying should be stable in 3 different axes. I will talk about this axis called pitch, roll, and yaw, which is X, Y, Z, 3 different axes that our airplane should be stable in these 3 axes. So for a stability, usually the tails of the aircraft are responsible for the stability. So for example, if we consider an airplane like this, here, stop share here. So this airplane is consisted of different parts. So here we have the fuselage, we have the wing, we have the horizontal tail, and we have the vertical tail, right? So this is one of the configuration of the airplanes that we have, and this is so important that this airplane should be stable in different axes. So I will talk with more detail about this. So if our airplane actually moving in this direction, so this is called pitch axis. If it move in this direction, it's called roll axis, and if it move in this direction, it's called yaw axis. So each one of these axes are so important once we are actually designing our system to be stable. So the stability requirements is depend on the vertical and horizontal tail. So if you look at this concept, this tail, which is a vertical tail, is responsible for the stability in the yaw axis, right, in the yaw axis. So we will discuss this with more details once we go to the stability analysis. So going back to our slides, the next step or the design requirement is the controllability requirements. So the system that we are designing should we should be able to control it easily. So the controllability is so important once you are designing in any aerial objects. So there are different control surfaces that we are going to talk about them, and these are the surfaces that we are using in order to control our drone. So if I want to show you here, these are the control surface that we have in this airplane. So one of them are the aileron. So one of them can go up and go down, and this is more for the roll control. We have here the elevator. As you can see here, this part of the tail, it's going up and down, and this is responsible for the yaw for the pitch control. It means that your airplane goes up or goes down. So this is something which is called control system. So we have the elevator here, we have the aileron here, and sometimes the vertical tail, they have a movable part which is called the rudder. So these are the components that we actually design for airplane in order to increase its controllability and somehow satisfy the controllability requirement. So the control surfaces are elevator, aileron, rudder, and also the aileron. Aileron is the combination of the elevator and the aileron, which I'm going to show you later on once you go to the design process of the control surfaces. And also another factor which is affecting on the controllability of our system is the weight distribution. So the weight distribution is another factor which is so important once we want to design our system. So for example, if I move the weight to the front part of my aerial object, my drone, so this is going to be nose down. So this is related to the stability that we'll talk about that later. So the flying quality requirement is something is important, which again affecting on the center of gravity and the weight distribution of our airplane. These are again related to the pitch stability, which we will talk about that later on. Airworthiness requirements. So for example, this would affect on a minimum safety requirement. So for example, if I have a drone which costs $100 or $200, so here we need to consider this, that what level of safety we need for our system. So for example, if we design a passenger aircraft, the level of the safety should be higher than a smaller drone, right? Because it's important. So here we are dealing with the life of the passengers and the payloads. But here, once you're designing an unmanned system, so nobody's going to hurt. So here, the level of the safety requirements is totally different in the different types of aerial objects. So the cost requirements is another factor which affects on our design. So for example, which affects on the materials, engine, and the weight. So for example, if we make an airplane, right, with a composite material or with aluminum, or for example, if you are dealing with designing a drone with the foam or the wood, so here the type of the material would affected by the cost requirement. So for example, this airplane that you can see here is made of the balsa wood and the foam. So this is going to be cheap. But if I manufacture this by fiber carbon or fiberglass or Kevlar, which are the composite material, so here the cost is going to be different. So, and the selection of the material eventually affects on the weight and the type of the engines that I am going to select. Because, for example, if I have the heavier airplane, right, with more expensive material, so I need to have larger engines, or I mean more powerful engines. Design duration requirement is something which is so important. Regarding the duration requirement, so here it means that the endurance, the flight endurance of our system. So for example, if you are designing a drone, a fixed wing UAV, which is flying for 2 hours, this is going to be different with another smaller drone like fixed wing micro vehicle, which is flying for 20 minutes. So what is important here is the configuration optimality. So it means that our system, the configuration of our aerial system should be optimized in such a way that our aircraft or aerial object can fly, with a higher endurance. So detectability requirement is something which is so important specifically for the military aircrafts or for military drones. So there are different stages that need to be considered once we want to detect our airplane. So this consists of the detection, the targeting, tracking, and attacking. So these are the 4 different stages which are important for the military aircraft. So once you want to consider the detectability requirement, we need to consider that what type of material should be selected for our aircraft, or for example, what configuration we are selecting for our airplane. So this would affect on materials and configuration. So this is some other parameters that will be affected by detectability requirement. So these are some components, major components, and these are requirements that we need to consider them once you are designing an aerial object. So during the design phase, there are also, as we said, there are different steps that we need to follow up after finding our design requirements for design and manufacturing of our aerial system. So if you want to summarize what we discussed here, there were 4 different steps for the design phase. The first one was conceptual design. The second one was preliminary design. The third one was detailed design. And the fourth one is the test and evaluation. So during the conceptual design, we are selecting the aircraft configuration. As I showed here in this concept, this is a different configuration of the plane compared to this one, right? So these are the two different configuration that we have here. So I am going to discuss it more detail about this later on. So during the preliminary design, we need to determine the aircraft maximum takeoff weight. So we need to have the weight estimation for our aerial object. We need to know what is the engine power or thrust, and we need to know the sizes of our airplane, the wing area or the wing span or the length of our airplane. So after this preliminary design, we will have the detailed design, which is composed of part 1 and part 2. In the part 1, we have the design dominant components such as wing, fuselage, tail, and propulsion system, and landing gear for our drones, that which I'm going to show you different components of this airplane. So this is going to be wing, this is going to be fuselage, this is going to be our propulsion system, this is going to be our horizontal and the vertical tail, and if our airplane have a landing gear, so it would have landing gear. But since this is a tiny UAV, this is just hand launch and it doesn't need the landing gear. So regarding the configuration, if you compare this drone with this drone, so you see that they have a different configuration. This is going to be a flying wing concept. It doesn't have the horizontal tail. It has a vertical tail, but it doesn't have the horizontal tail. But this one, the configuration is different. So this is something that we need to consider during the design process. So going back to the part 2, we have the design servant components such as the landing gear, engine structure design, the cabin, the avionics system, electronic system, and the air conditioning system, which is more for the passenger or manned aircraft. So these are all the components that we need to consider once you are designing our aerial object. So the last step is test and evaluation. So here during this design process or design phase, we are running different types of aerodynamic analysis. So for example, how much lift we can get from our wing, or how much drag force is generated by our configuration of our airplane. So we can also run different types of the wind tunnel testing. We can do the aircraft flight dynamic testing that makes sure our aircraft is stable. And we also need to consider the aircraft structural testing, and these are the propulsion system. So again, going back to this slide, we had 4 different design phases, including the conceptual design, which we specify the configuration. We have the preliminary design, which we determine the aircraft maximum takeoff weight, engine power or thrust, and also the wing reference area. For the detailed design, we have 2 parts. In the part 1, we are specifying the design dominant components such as the wing, fuselage, tail, and propulsion system, and landing gear. In part 2, we have the design servant components such as landing gear, engine, structural design, cabin, our avionics system, electronic system, and air conditioning system, which is more, as I said, for the passenger aircraft. And then during the test and evaluation, we are running different types of aerodynamic analysis in the software or in the wind tunnel using the model of our system. And we need to run our flight dynamic test, our structural test, and the propulsion system test. These are the varieties of the tests and evaluations that we need to consider before designing any aerial object. So going to the next slide, again here, this is a flow chart which identify different phase of the design. And actually, this is a detailed design process. So we had the needs, we had the conceptual design, we had the preliminary design. And after the preliminary design, these are some steps that we need to consider. So design of the wing, design of the tail, design of the fuselage, design of the landing gear, design of our engine, and then We will do the design of the other components. In the case that we have a passenger aircraft or a manned aircraft, we will calculate the drag force, and we evaluate the performance of our system. We will fix the weight distribution. I mean, somehow the center of gravity. We will evaluate our stability criteria. We will design our control system, the controllability evaluation that we will do, and eventually we have the test and final evaluation of our system. So this is a summary of all the design phases that we have. So during the design phase and the test evaluation, I mean, after the detailed design and manufacturing process of our aerial object, we need to have the design, we need to have the test and evaluation. So as we had before, we had the design requirement as the first step of our design. We had the configuration design, which was a conceptual design phase. We had the preliminary design and the detailed design for our system. So after this, we need to somehow manufacture our system and run different types of analysis and the testing. So here we had, we can have a wind tunnel testing. As you can see here, we can have the flight test. We can manufacture our airplane or the drones and test our system. We can have the engine test. As we can see here, this is our engine that we are going to test our engine. And we have the structural test that we are going to test the structure of our system, or the test the material or different component of our system. And eventually, if this passed all of these tests successfully, we have the certification for our drone, and it can go for get the certificates for different components for actually from the FAA to use our flying system. So these are the different tests that I showed you here. Some of them, they are done on the lab. For example, the wind tunnel testing, the engine testing, and structural testings. Usually these are done on laboratories, and a flight test in the runway, which is running the actual test of our aerial vehicle. So in order to design process of any aerial object, these are, we need to know that who should work on what concepts, or who should work in what stage of the design. So this is a work breakdown structure based on the aircraft components during the design phase. So we have usually wing design team. There is a team which is just actually designing the wing. We have the tail design team, we have the fuselage design team, we have the landing gear design team, we have the propulsion system design team, we have the equipment design team, and we have the drawing and the drafting. So work breakdown structure based on the discipline during design phase is a structural design team, aerodynamic design team, a stability and control team, the performance analysis team, airworthiness team, FAR, the weight distribution, and again, drawing and drafting. So these are the different categories for the teams that they're working together to design an aerial object. And then organizational chart during the fabrication phase. So we have the assembly and integration. We have the structural team. We have the mechanical system team. We have electrical systems. We have the certification group, flight test group, and equipment group. So these are different groups that after designing and manufacturing, they are assembling different parts, run different types of testing, and then they're working electronic or avionics system, and then finally getting the certification and testing the airplane. So there are major differences between the manned and unmanned aircraft system that I am going to discuss this with more details. So there are major differences between manned and unmanned aircraft design that I am going to discuss in this lecture. So if we consider unmanned system like the aircraft that I showed you here, this airplane, and also the manned aircraft, there is a big difference on the components that we are considering during the design process. So the first major difference between the manned and unmanned aircraft design is the mission. So the mission that unmanned systems like, for example, the quadcopter or the flapping wing drones have are totally different with the manned aircraft like the passenger aircraft or military aircraft or the huge unmanned aerial vehicle that they are applied for the military missions. So for example, if we design a passenger aircraft, the type of the mission for the passenger aircraft is different with the design process of the drones. So for example, these type of drones are for search and rescue, but this is for carrying the passenger. Or for this is a firefighter, which the mission is different. So then based on the mission, the configurations are different. So for example, if we compare this passenger aircraft, the shape of the fuselage, the configuration of the airplane is totally different with the military aircraft. Or it's different with this flapping wing, hummingbird inspired drone, or with this hexacopter or this multi-rotor. So the configuration, this is a VTOL, vertical takeoff landing system. This is a fixed wing system, and this is a flapping system. So the configuration is totally different based on the mission. So having different configuration, we will have different proportion and energy resources. So for example, this is using the 2 engines or ducted fan for propulsion system, and the type of the fuel for this aircraft is going to be fossil fuel. But if we get back to this smaller drone, you'll see that this flapping wing drone, the propulsion system is generated by a small motor and actuation mechanism, which provide the flapping motion. And also we are using batteries as the sources of energy. Or this quadcopter is using for 6 engines, or a hexacopter is using 6 engines for the vertical takeoff landing fly, and the energy resources again is a battery. The weight and size again is different. So for example, these are the heavy airplanes. This has the lower weight, this UAV, than this passenger aircraft or this military aircraft. And this flapping wing is maybe 10 grams or 20 grams, which is so small and has a lower weight. Again, depend on the mission, where we are going to do our mission and what type of the configuration that we have, the weight and the size are different. Aerodynamics are again a factor which is different between the manned and unmanned aircraft. So for example, these airplanes, this military aircraft is flying with a higher speed. So we are dealing with a supersonic or hypersonic flight. But if you consider this, for example, hexacopter or this fixed-wing UAV, they are flying with a lower speed than this military aircraft, so that the type of their aerodynamics is different. And this flapping wing, which is inspired by hummingbird, is flapping with the higher frequency. It means that they are flapping with the higher frequency. And we are dealing with the unsteady flow or unsteady aerodynamic, which I am going to discuss this with more detail in future. The type of the control mechanisms are different. So for example, the type of the control surfaces that this military aircraft has is different with the control surfaces of this flapping wing. The endurance is different. So for example, this passenger aircraft can fly for 15 hours or for 12 hours, or compared to this military aircraft, usually they don't need for the refueling system. For the short flight, but for these tiny drones or tiny flapping wing nano aerial vehicle, or for this hexacopter, their flight endurance is around 20 minutes to half an hour. So because the type of the mission that these type of drones or aerial objects are used are totally different with the passenger aircraft or the military aircraft. The type of the payload is also important. So for example, if I consider this hexacopter, the payload is just a camera, but the type of the payload that this aircraft is using, the passenger aircraft is using is totally different. I mean, these are the passenger, or the military aircraft, they are carrying the weapons. The safety and reliability is something again different. So for example, the safety of the passenger aircraft is more than military aircraft, and also the safety of these two manned aircraft is also more than this unmanned system. So these two manned aircraft, they are more also reliable than this flapping wing, tiny flapping wing drone, or for example this hexacopter. And also the type of the subsystems that we have, this is another difference between the manned and unmanned aircraft. So for example, this type of drones, they don't have the landing gears like the landing gears of this firefighter or like this passenger aircraft, or for example, the type of the weapon that they are attached to UAVs are different with the type of the sensor that you are attaching to these drones. The type of the navigation system, the type of the propulsion system, the type of the cameras, and the type of, for example, different subcomponents are different in this unmanned system with this manned system. So these are the major differences between the manned and unmanned aerial vehicles. So I want to now talk about different types of the drones, and also talk about the development of this drone industry. So nowadays, due to the advances, because of the design process, because of the manufacturing material, because of the guidance, navigation, and control method, which is called GNC, and the power storage system, we have a wide range of the drones. So because of these advances in this parameter, we have the development of the wide range of the drones. As we can see here, we have different configuration and different shapes for our aerial systems. So for example, once I'm talking about design process, we talked about 4 different stages in the design, including the conceptual design, the preliminary design, the detailed design, and test and evaluation. So we have different flow charts can be applied for the design process of the aerial object. So for example, design can be based on the mission, or it can be based on the engines, or based on the equipment that you have, or based on the structure. So there are different methodologies for the design process. And also we have the varieties of material, and the manufacturing process can be employed in order to design the different types of the drones. We also have different guidance, navigation, and control system. So for example, we'll see this kit, which is controlling the drone by its brain. There are different methodologies for controlling the aircraft. So for example, if you have the unmanned system, we can control by a remote controller or radio control, or if we can control by our vision base, by a camera, or we can control by our brain. This is a new novel concept that you can see here. This kit is thinking, and our brain is generating some electromagnetic waves, which can be eventually translated to some code, and this code can be implemented on drone in order to control the drone. Or for example, one of the problem of the aerial system, specifically unmanned system, is their flight endurance or the flight time. So one of the solutions that has been proposed is that researchers design a high power laser beam, which are locking to a small solar cell at the bottom side of the airplane in order to provide the necessary energy and to charge the batteries of our system to keep it for the air for whenever we want. So there are different ways to increase the endurance of the aerial system that we are going to talk about that, I mean, in another lecture. So drones can apply, for example, the solar cells in order to fly during the day, which receiving the sun radiation in order to charge their batteries. But during the night or once the sky is cloudy, so we cannot use the solar cells because there is no any radiation can be received by sun. I mean, can be received by sun, I mean by the drones from the sun. So what's happening here, the researchers proposed this, instead of putting the solar cell at the top, which we don't have a control on the radiation, we can have a system which is mounted on the ground station and can lock laser to the drone and charge the drone for in the sky. Since this is in the ground station, so we have a control on that, and we can provide energy as long as we want for our drone. But there are some challenges with this system. The first challenge is that the controlling drone in such a way that the laser can be locked on the solar cell is so complicated. And the second challenge is that this type of drones, they don't have the higher range of the flight because the laser cannot reach, for example, 20 miles or 30 miles. So this is usually for 3 to 5 miles that their system can be applied. So there are different classification of the drones based on their configuration and based on their size. So this is one of the classification that I have proposed for the different categories of the drones. Let's start from the UAV, unmanned aerial vehicle, to the smart DOS, which they are in the DOS size and they are not visible. So in this spectrum, we have the UAV, which is the abbreviation of the unmanned aerial vehicle. We have the micro UAV, which is called micro unmanned aerial vehicle. We have the three classes of the micro drone, including the micro aerial vehicle, nano aerial vehicle, pico aerial vehicle, and the smart DOS, which they are in the DOS size and they are not visible, but they can do whatever drone is doing. So in this classification, we have different categories. We have HTOL, which stands for horizontal takeoff landing. We have VTOL, which stands for vertical takeoff landing. We have tilt rotor, we have tilt wing, we have tilt body, we have the ducted fan, we have the helicopter, we have the heli wing, and unconventional drone. For the micro UAVs, we have again HTOL, VTOL, tilt rotor, tilt wing, tilt body, ducted fan, and we have a new classes which is called cyclocopter. We have the flapping wing, we have the onicopter, and we have the helicopter. So I'm not going to discuss about the rest in the next slide. I'm going to show you some picture of if different categories maybe be more visible. So if we consider the drones, as we discussed in the previous lecture, they are classified from based on their wingspan and based on their weight. So they are classified from the huge UAV with 61-meter wingspan to the smart DOS, which they are in the size of the 1 millimeter. So the UAVs ranges from 61 meter to 2 meter wingspan and a weight of the 15 tons kilogram to 5 kilogram. Micro UAVs, they are similar to the UAV as we can see here, but they usually have a lower weight and lower dimension, and they are hand launched, and they are launched by our hand. They have a dimension between 1 meter to 2 meter and a weight between 2 kilogram to 5 kilogram. We have the micro aerial vehicle, which they have the size between 15 centimeter to 1 meter and the weight of the 50 grams to 2 kilograms. We have the nano aerial vehicle, which they are mainly flapping wing and inspired by small birds or huge insects like dragonfly or butterflies, which they have the size of 2.5 centimeter to 15 centimeter and the weight from 3 grams to 50 grams. We have the pico aerial vehicle, which they are the insect-sized drones, which they have the weight of the half a gram to 3 grams and the size of 0.25 centimeter to 2.5 centimeter. And eventually we have the smart DOS, which they are in the size of 1 millimeter to 2.5 millimeter and in the weight of 5 milligrams to half a grams. So these are the different categories that we have for the drones, and here these are these different classifications that we have the spectrum for that, and we have different configuration for each classes. Regarding this, these are considered bio drones. So if you want to design a flapping wing in the size of the insects, there are lots of challenges for this type of the drones. Due to this, researchers came with this idea that instead of designing and controlling the smaller, tiny insect-sized drones, we can control the live insects like this beetle or this mosquito in order to use them as a drone. So I will discuss it more details about this concept, that how this is going to work. Or for example, this is a pigeon that they implement a small sensor at its brain, and they are trying to control the brain of this pigeon and use that as a drone. This is not moral, but this is something that's happening in the world, and they are using the animals in order to use them as a drone. This is a flying cat, which has a story behind this. This is a taxidermy cat, which I am going to discuss about that. So there was a guy in Germany. He had this cat as his pet. So the guy in 2011 was doing an aerospace degree, and he had this cat as his pet. So one day the cat hit by a car and passed away. So he was so sad. Then he had a son. They did a brainstorming. The guy also was an artist. They did a brainstorming, and they taxidermied the body of this cat, and they put 4 motors in the legs and the hand, and it made it flyable as a flying cat. So this concept is not moral, because the main reason is that this is a taxidermy, this is a dead body of the cat, but there is something scientific behind this. So we know that if a cat jumps from a building with a 30-meter height, it will die. But if this cat jumps from a building with 50 meters, it can survive. The main reason behind is that once the cat is jumping from the higher building, it has a time to open its legs and the hands in order to glide. So it will fly like a glider or a parachute. And this is the main reason that it can survive. So the body of this cat is so aerodynamics, and I consider this categories as the bio drones, which is a combination of the birds, insects, and other species of animals with some sensors or electronic equipment. Drones have 200 applications. Depends on the flight zone, depends on the mission, depends on the environment. The drones can have a varieties of applications. So for example, if we design a drone which is flying in the outer space, this is going to be different with the drones which they are flying in the indoor space. So for example, if I show you, this is a flapping wing drone. This is a flapping wing drone, which is a tiny drone. So this is inspired from the birds, and it can fly in indoor space, for example, in this my office. Or for example, it can fly in the outdoor, right? This drone, which is a fixed wing micro aerial vehicle, this cannot fly in this indoor space. So this is made for outdoor space. So the configuration of the drones is totally affected by the type of the flight zone that they are flying. The mission, for example, if you are using for military or civil, we can have a varieties of applications. So for example, for military, they can be used for missile launching drones. We can have bomb dropping drones. We can have flying camouflage drones. We have a communication disruptors drones. We can have a battlefield medical supply drone. We can have invisible spy drones. We can have a solar power, high altitude Wi-Fi drones. We can have aviation or delivery drones, and we can have landing field drones. For civil application, we can have for videography or photography, can have for disaster response, city or government application, for environment and climate monitoring, for construction drones. We can have space drones. We can have mining or oil gas drone. We can have drones for inspection, for maritime, for meteorology, for agriculture, for hobby, for mapping, and for miscellaneous applications. So these are the varieties of applications that drones they can have. And also drones, application of drones based on the environment is different. I mean, the drones which are moving under the water or over the water or under the ground or in the air or the space are different. So for example, here this is an Amazon drone, which is for cargo delivery. And this is a search and rescue drones that you can see here. So they have a varieties of applications that we will talk about them with more detail. And I will show you some cool stuff and cool videos about the applications of the drones. So this slide shows the cost and investments on the drones industries. So drones will change the world in future based on the varieties of application that they can have, and they will be everywhere. I mean, we are thinking about next 100 years, so everything is going to be robotic eventually, and so drones can play an important role in the future world. So because of this, drones market shows a positive outlook with a strong industry growth. So if you look at the price in the investment on the drones, $10 billion in MQ-9 or Global Hawk drones is one of the biggest fixed-wing UAV that we can see. And this goes to the tiny drone, which is a smart dust. You will see that these are like the size of the dust particle. They can be equipped with the solar panels and with some energy harvesting techniques that they can be controlled on the environment, and they can gather information from the environment. So a smart dust was a project proposed in 1998 by Professor Priester in Berkeley University in California, which came with this idea that create some particles or some MEMS or NEMS technologies, micro electromechanical system or nano electromechanical system, some tiny sensors that they can actually measure the temperature or pressure of the environment. And eventually came with this idea that this can have other application, including military application, that this tiny dust can be applied for environmental protection or for the varieties of applications. So you see that the price of this smart dust projects is actually more than the rest of these tiny drones and is less than this actually big UAVs. So this shows that how actually increasing the size or the weight of the system and decreasing the size and the weight would increase the price and the cost of our drone. So thank you for your attention. This was one of the lectures that we had today, and we discussed today. And in the next lecture, I'm going to show you different categories of the drones and show you some nice pictures of each categories to see that how we can proceed with the design process of the varieties of the configurations that drones they can have. If you have any question, please feel free to contact me through the email, or you can reach me through my phone office number is 575-835-6903. So feel free to reach me if you have any question, or directly send me an email. We can meet and we can discuss more details about the materials that we covered here. And in case if you have any question, feel free to reach.